Okay, I'll get started here. Today we're going to be talking about more reinforcement learning, and we're going to be talking about Monte Carlo methods, which are not specific to reinforcement learning. They can be used for many different things, but we'll introduce what they are and then how we're going to use them to help solve reinforcement learning problems. Excuse me. Monte Carlo methods are chapter 5 in the reinforcement learning textbook, so if this kind of thing excites you, then go read as much as you like about them, or feel free to use this to help study for the exam if you want. But I'm just going to be covering a small subset of what it talks about in the book for Monte Carlo methods. So Monte Carlo methods are, at least in the context of reinforcement learning, they're methods for estimating value functions and discovering optimal policies. So there's a way that we can solve reinforcement learning problems. Unlike dynamic programming, which we talked about last time, we do not assume complete knowledge of an environment, and we don't need a model of the environment. So we can just take samples of things and then update our beliefs, and we don't need to know exactly how that model works like we do in dynamic programming. Monte Carlo methods require only experience. So in the context of reinforcement learning, that means a sequence of states, actions, and rewards from either an actual environment or a simulated environment. What do I mean by that? So an actual environment or actual experience would be something like a human being, a physical robot in an environment, etc. Versus a simulated experience or a simulated environment, we could talk about like a video game or a simulation running in code. And so learning from actual experience does not require a model of the environment. That is a very, very important point because it actually lets us do reinforcement learning in the real world. Despite our best efforts, we don't have a complete model of the physical world, right? We have some formulas and some estimates at things, but we don't have the exact model. But we don't need to know the dynamics, the physics, the layout, or the full state space, etc. All we need to be able to do is take an action, carry it out, get a reward, and then update our beliefs of how good doing that thing is, right? So we are capable of learning in the real world through a process which I think is very similar to reinforcement learning, and we don't know a model of the environment, right? We can know that something, we get a particular reward without knowing exactly why that may be. In a simulated experience, like a video game or a computer simulation, learning from these simulated experience is also powerful because we don't need to know how the model works. We only need to know that state transition function, right? So what do I mean by this? So for example, if we're playing a game like any of the Mario games, for example, we do not need to have access to the game engine like we would with something like alpha, beta, or A star, where we would need to know, okay, if I do this action, what state will I end up in? All we need to know is, okay, I've done this action. Here's the new state that I've experienced in the game and what the reward was from that. So it's a bit of a distinction. So Monte Carlo methods don't need to know all the action or state probability distribution functions, whereas dynamic programming does. So we need to know exactly what's going on with the environment in order to use dynamic programming, which we don't always have access to. In fact, most of the time we don't have access to. So in practice, we very rarely get to use dynamic programming for reinforcement learning. So Monte Carlo methods all use the process of sampling. And so sampling is essentially you get data somehow, whether those are randomly generated or through trial and error. You're just getting samples, and then you're updating your belief of something based on those samples. So here's a really cool example of Monte Carlo methods. Here, what we're trying to do is estimate the value of pi using a Monte Carlo method. So what happens is we have a square, and that square is, let's say, for example, length 1 by 1. And then inscribed inside that square, we have a circle. And since the sides are length 1 of the square, then that means the radius of the circle is 0.5. And so the square area is 1 times 1, which is just 1. And the circle area is pi over 4. So what we can do is we can say, okay, let's generate a bunch of random points within this square. right? So we all know how to do that. We can use math.rand. We generate a bunch of points within the square, and then we can tell whether or not the point that we generated was inside the circle, because we can just see if the distance from the center is greater than the radius. And so what we have here is after we've generated a bunch of random points, we can see the ratio of the amount of points that were generated randomly inside the circle versus the number of points that were generated in the square but outside the circle. And since we know the ratio of the area of the circle to the area of the square, then we can have an estimate of pi. So approximately, pi over 4 is approximately the number of points that were inside the circle that we generated divided by the number of total points that we generated. And so we just say, okay, 4 times the number of inner points divided by the number of total points, that is approximately pi. And what we get over time is something like this, where we run a simulation and we calculate that value, and over time, as we generate more and more and more points, we get closer and closer to the value of pi. And so we can set up all sorts of cool environments like this where we use effectively random sampling to help us solve a problem like this. And the idea here, of course, our random samples would have to be uniformly distributed, right? So the assumption here is that any of the points within this square have an equal chance of being chosen. If they didn't, then the ratios would be different and we wouldn't be able to apply this formula. Another example, a bit of a harder problem, is trying to estimate the area under a curve. So if I give you a function, give me what is essentially the integral of that function. What is the area under the curve between 2 points? So how would we do that? Well, it's essentially the same problem as the pi one. So let's generate a randomized amount of points in an area. So over here, for example, I have this rectangular area. I'm going to generate a bunch of points. And then whenever I generate a random point, I can use the function, which I know, so I can evaluate f of x. So if I have this x value, right, I evaluate f of x to give me the value of the function, and then I know the y of the randomly generated point, so I can tell whether or not the generated point was above or below the line. And so since I can really easily calculate the area of the entire rectangle, then the area under this is the ratio of the total points that were above the lines to the total area of the amount of points that were below the line in compared to the amount of points that were above the line. And so as we do this more and more and more times, we can see that we can actually generate a good estimate of the area under a curve. And this can work for arbitrarily complex functions. The only thing is that, of course, it has to be an actual function so that for each x, there's only one possible y value. But this is just some examples of Monte Carlo methods that use this process of random sampling to solve much more complicated problems. Now, I say solve, but this is all, of course, within some amount of error. You're never going to get the exact number using Monte Carlo sampling. But what you could do is, you could generate a certain number of points. Maybe you generate 1 million points, or you stop once the difference becomes really small or something like that. But this is what Monte Carlo methods do, at least outside of the process of reinforcement learning. So Monte Carlo methods are able to solve reinforcement learning problems using samples, okay? Especially in cases where there's randomness involved in the environment. So it learns based on averaging the sample returns, and we know what that means now because we looked at that in the last lecture. And so we will be discussing Monte Carlo methods for episodic tasks. So all of the experience is divided into these finite episodes, and these episodes eventually terminate. And so value estimate and policy updates are performed at the end of an episode. So in Monte Carlo methods, we do an entire episode, and then we do our updates. And I'll show you the math behind that in a little bit. So Monte Carlo methods sample and average returns for each state action pair, just like bandit methods do. So it's kind of similar to what we did last time, just a small extension. And Monte Carlo methods essentially treat each state as one of those bandit problems. And because each of these bandit problems are related, because their returns after actions depend on the neighbor future actions. So that was what we talked about when we did dynamic programming. So the goal for Monte Carlo prediction, prediction means what is the state value. We're trying to predict the value of a state or a state action pair. The goal is to learn state values for a given policy. And the value of the state, as we talked about last time, is just the expected return. So the sum of discounted rewards starting at a given state. And here's the intuitive way that we could use Monte Carlo methods to obtain a state's value. And again, this is very similar to what we did last time. It's just using Monte Carlo methods instead of the standard bandit problem. So we're going to carry out an episode, for example, maybe a hand of blackjack or a run through a maze. Then we're going to record all of the states that we visited in that episode. So I was in state X, I was in state Y, I was in state Z. And then we average the return after visiting each of those states. And then after the episode is finished, we update the value estimates of the states with the average return obtained in those states. And so this will be, and over time, this is going to converge to the actual expected value. And so I'll show an example of this with Blackjack in a bit where it should be more intuitive. But basically what you do is you carry out an entire episode, you figure out the total rewards that you got from that episode, and then for each state that you visited in that episode, you do the bandit update that we learned last time. Okay? All right. So some syntax notes. The value is an expected return from a specific situation. V pi of S, that's the expected future return when starting in state S and following pi. Talked about that last time. And Q pi of SA is the expected future return when starting in state S, taking action A, and then following policy pi. So we're going to need these in the upcoming slides. I just wanted to remind you about those values. So let's do an example of blackjack. So blackjack is played in hands. Does anyone here not know the rules of blackjack? Okay, so a couple of people. Okay, essentially, do I have the rules of blackjack? Yes. Okay, I have a slide on that. So the reward is going to be 0 at every state except the terminal state, right? And so at some point in a hand of blackjack, you are playing against the dealer of the casino. It's a gambling game. And at some point, excuse me, the hand is going to end, at which point it's determined whether you've won, you've lost, or you've drawn the game. So I'm going to bet $1. We're going to play a hand. If I lose, the casino keeps the $1. If I win, the casino gives me $2, so I've won $1. And if we tie, then I just get my $1 back. Okay, so that's essentially blackjack, and then there's some rules. So winning is going to get +1 reward, and a loss is going to get -1 reward. There's a special rule in blackjack where if you get a blackjack, which is a 10 and an ace, then you get a +1.5 reward. So it'll be 1.5 instead of 1 as a reward for a blackjack. So in blackjack, just a refresher of the rules, many different players can be playing blackjack. So you can have 8 people playing against one dealer, but essentially, the fact that there's 8 people doesn't mean anything. Okay, it's essentially 8 1 versus 1 games. They're not actually colluding, or they're not playing with each other or against each other. It's just each separate player is playing against the dealer, and the casino wants to make a lot of money, so they let a bunch of people do this at the same time. So you can essentially view blackjack as you with some cards against the dealer with some cards. So the cards are shuffled, and then they are dealt to the dealer and the player. So the dealer gets their cards. It doesn't really matter in what order the cards get handed out. I'm just drawing them in this way. So the dealer gets dealt 2 cards. One of them is face down, and one of them is face up. And this kind of creates the drama of blackjack, is that after you have decided on your actions, the dealer's card is going to be revealed, and then the game is going to play out and say whether or not you win or lost. And so that's where the drama of blackjack comes from. Otherwise, if you could see both the dealer's cards, it would be a very boring game. So then the player gets dealt 2 cards. And these cards, you're going to take the face value of those cards and you're going to sum them up. So for example, right now, I have 7. and I know that the dealer has a 4. So most likely, what the dealer has is 14, because there are more 10 cards in the deck than any other card, right? So it's more than likely that the highest probable value that the dealer has is 14, and then they could have, if they had a 2, they could have 6, 7, 8, 9, all the way up to 15 if they have an ace, right? So the dealer could basically have anything. And so I keep getting, when I am in this scenario, my 2 choices in Blackjack are either hit me, so I say hit me, in which case I'll get dealt another card, or I can say stick, in which case I keep the cards that I have and no other actions are taken. Once I stick, once I choose that I don't want any more cards, then the dealer's card is revealed, and the dealer has to keep hitting until they have 17 or higher. And the goal is to get higher than the dealer's hand without going above 21. If at any point my cards sum to more than 21, I instantaneously lose. Okay? So I'm trying to get as higher than the dealer without going over 21. And so the actions that I take will be dependent on the card of the dealer that I see. So if the dealer has a 4 showing versus the dealer have a 10 showing, my actions should be different, because if the dealer has a 10 showing, it's more likely they have a higher sum, and so I need to bet a little bit, or I need to take a few more cards. So in terms of Monte Carlo, what's happening here is that we are now at state 0, right? So there's going to be an episode. That episode is going to have a number of states in it, a number of actions in it, and a number of rewards in it. So this is state 0, where I have a 7, or I have 7 total, and the dealer has a 4. So I'm going to represent this as state 0, I have a 7, dealer has a 4. Okay? Now, if we were using a table to update our values, we could have a 2D array indexed by my card sum and the dealer card sum. I could convert that to a 1D array. I could use a neural network to store that. Doesn't really matter. But I'm going to represent it as my card, or my sum and the dealer's sum. So that's state 0. And now the actions I have available to me are hit and stand. And if you've played Blackjack like in an actual way, you know that there are actually more actions than this. I could double down or split, but those are just extra actions that specific casinos use. We're going to simplify the game so that my slides aren't too complicated, right? So I can either hit to give me another card, or I can say stand to stay where I am. So let's say that we have some policy already. Maybe it was randomly generated. Maybe it's the perfect Blackjack policy. I don't know, but I have some policy pi. And then of hit and stand, what I have chosen to do at this time is to hit. And so A0 from S0 is hit. Okay, so that's the way that we're representing these things. Now, because I've chosen to hit, the environment changes. I take an action, the environment does something, it gives me another card. And since this is not the ending state of the game, my reward for taking that action at that state was 0. Okay, so my reward, my R1 is 0. So I got a 2, I haven't busted, so I'm at a 0. Busting means going over 21. Now, here is my state. I am now at state 9, 4, because the sum of my cards is 9, and the dealer doesn't get any cards until I've finished my actions. So I just got a reward of 1. Now what I'm going to do is go to my policy and find what should I do when I'm at 9, 4. Well, maybe it says with 80% chance you should stick, and with 20% chance you should hit, and with 20% chance you should stand. So whatever the policy says, we ended up hitting. And so because we hit, we get the environment updates, and so we get a 5. And so now the sum of my cards is 14, and so we're now at the state 14, 4. And because the hand hasn't ended yet, I get a reward of 0. So a lot of games only really have a reward at the end of the hand, at the end of the episode. Let's keep going. So 14 against 4, I've chosen to hit again. The environment gets updated. Ooh, I get lucky. I got a 6. So now I have 20 to the dealer's 4. I still got a 0 reward, and what's going to happen now is I'm going to choose to stand, right? Because anything, any card except an ace will put me over 20, so I have a very high chance of busting if I don't stand now. And so this has been a decent strategy that we've followed so far. So now what happens is, immediately after I stand, the dealer has a fixed policy. And so the dealer is not, this is not a two-player game. This is essentially a one-player game. Because the dealer doesn't get any choice in its actions. Its policy can't change. It's just part of the environment. And that says it is going to keep getting cards until it gets to 17 or it busts. So the dealer has to hit until greater than or equal to 17. So it gets a 3, and then it gets king. And so it had a 5, so now its total is 22. So the dealer busts. So my reward from performing stand at 20 and 4 is 1, because it took me from this state, so performing A3 as stand at state S3, which was 24, takes me to the state win, right? Because it doesn't matter which winning state I'm in or which losing state I'm in. Going to the winning state from any state gives me a reward of 1. But maybe this had happened instead, where the dealer got a 9 and got a 21, which always happens to me, and probably you if you actually play Blackjack. And so what has happened here is instead of going to the winning state, we've gone to the losing state. Okay? So our reward for going to the losing state is -1 instead of 1. But maybe the other possible outcome is that the dealer got a 20, which is called a push, which means that we tie. And the reason it's called a push is because the dealer just pushes our money back to us and no money changes hands, just a tie. So the reward I get from a draw is R4, which is 0. Okay. So let's look at this numerically now instead of visually. So the player got dealt a 4 and a 3, and the dealer was showing a 4. So state 0 over here, 7-4, action 0 was hit. I got a 2, so the reward was 1. The next state, therefore, since I got a 2, 7 plus 2 is 9, so now I'm at this state. I chose to hit. I got a 5, reward is still 0. 14-4 is the next state, hit, get a 6, reward is 0. Then at 24, I chose to stand, and this led to 1, because I ended up winning that game. So the dealer policy led to busting in that episode, and so I went to state 4, which is winning. But because there's randomness in Blackjack, it could have been either of those scenarios where I won, lost, or drew that particular game. Okay? So the state sequence of that episode is as follows. I started in state 0, went to state 1, state 2, state 3, state 4. The action sequence of this episode was hit, 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 stand. Or if we're representing hits or stands in some program, maybe we have 1s or 0s. So this would represent me getting a new card, new card, new card, stick. The reward sequence would then be 0, 0, 0, and 1. But an important thing to note is that the future reward sum of every state is 1. Because what the future reward sum means is that what was the sum of my future rewards from each state? So the sum of my future rewards from here is 0 plus 0 plus 0 plus 1. Sum of my future rewards from here is 0 plus 0 plus 1. Sum from here is 0 plus 1, and of course from here it's 1. So the future return sum of this episode is this. Okay, so this is how we would numerically look at this episode. So if I have this state sequence and this action sequence, and so now what I would do is after the episode is over, I have these state action pairs, right? So I'm at this state with this action, and so I'm going to update. So remember when we did the bandit update, when I took an action and got a reward, then I did either the incremental average update or the average future reward or the fixed size alpha or whatever. So I'm at state 7-4, and I've taken action 1, so that's my QSA. So I update my belief, this is going to be some floating point number, and I'm going to pull that belief closer to 1. Because I just won with that hand, so now I think that that hand is, or doing this at this state is better. And so for each hand in the episode, or for each state in the episode, apologies, I do that. So for each state action pair that I saw, so 7-4, 1, 9-4, 1, 14-4, 1, 24, 0, I update these things. So essentially what it's doing, in a nutshell, is saying, okay, if throughout that episode I took a particular action at a particular state and I ended up winning, then update my belief of the value of doing that action at that state to be a little bit better. Right? So if you keep winning by doing a certain thing at a certain state, then it's probably really good. And if what I did was actually bad, but I just got lucky on this state, then the next time I do the same thing at the next state, I'll probably lose, and it will pull my value down. So as I keep getting these samples, as I keep doing hundreds of thousands or millions or tens of millions of these, what I will arrive at are the true values of being at this state and taking this action. And so what I can do then is look over every possible state and choose the action with the highest value, and that will give me the optimal blackjack betting policy. And so this is how you would use Monte Carlo to solve blackjack. Or if you wanted to update, instead of QSA, the V pi of S, so these are the state values rather than the state action pair values, you just do that for the actual state in your V array rather than your QSA array. Okay, so that is called every visit Monte Carlo prediction, where you're trying to find the value of Q pi of SA for all the states and actions in your environment. So here is the pseudocode for that. We will not be implementing this on an assignment, but of course it's fair game for the exam. So every visit, what every visit means, we're about to do first visit, and so there's a bit of a distinction there. But what every visit means is that right here, wherever we saw a state action pair, if we see that state action pair multiple times, we do the update for every time that we see it. In the next algorithm, which is the first visit Monte Carlo, which actually performs a little bit better, what you would do is, when you see a state action pair, you only update the first time that you see it. So every visit, update every time. First visit, only update it the first time. So here's the algorithm. So we've got every visit Monte Carlo, we have to be passed in a policy pi. So we have our QSA values. Those are the initial values for the state action pair. How we got those, we're not sure just yet, but we have them. And so what we do is we are going to keep track of the returns that we got for each state action pair in the environment. And then while true, so while true means we're going to keep learning. What we're going to do is we're going to generate an episode. So generate an episode with our policy, which we just did. That was the blackjack example. And then that episode is going to give us state, action, reward, state, action, reward, state, action, reward, all the way up to the terminal part. So that is the hand of blackjack that just got played. Then, that line skip is intentional. I'll show you why in a bit. So for each time step in the episode, what we're going to do now is we're going to go through each state action pair and update the value based on the final return that I got from that episode. So for t equals 0 to capital T, that means from time step 0 up until the end of the episode, we'll calculate the sum of the rewards that I got from this state to the end of the episode. Then I'm going to append that return to returns STAT. So that keeps track of all the returns that we got at that state doing this action. And then what we do is I say, okay, my new value that my new estimate for the value of doing action A at state S is just the average of all those returns. Okay? So I'm just keeping track of everything that I've ever done at that state, the return that I got from doing those things at that state, and so my belief at how good doing that action at that state is just the average of all the things I've done at that state and the reward that I got. So that's it. That's pretty intuitive, right? You go through all the things that you did at each state and you average the returns that you got. So we want to estimate this either the value of a state or a state action pair given a set of episodes by following a policy pi. So each occurrence of a state S in an episode is called a visit to S. And each state may be visited multiple times in an episode. So in Blackjack, our sum can really only go up. So in Blackjack, we can't visit a state multiple times. But you could think of in pathfinding, we could visit a state multiple times, right? We could go up, right, down, left, and then we're at the starting state. So in many different problems, we could actually visit a state multiple times. And so what we just saw was every visit, MC. And so first visit Monte Carlo methods estimate V as the average of returns following the first visit, whereas every visit Monte Carlo methods have different theoretical properties, and we're not going to actually be using that. It's better to use first visit because of their theoretical properties, which I'm not going to get into in these lectures. I'm not going to bog you down with too much of the mathematics. So every visit MC may update a state value for a single state multiple times if it's visited more than once during an episode. And this is not always desired, since the first visit will contain a deeper return calculation than subsequent visits. So what that means is, like, if I saw a state at like time step 2, and then later on I saw it at time step 90, out of 100 total time steps, then the return that I got from being at state 2 is, it tells us much more about that full 100 time steps than the second one. So basically what it's saying is that the first time you see something, its return is a much more valuable calculation than the one we'll get from a later one. And so try only updating states on first visit if you're doing Monte Carlo. So where we just had every visit Monte Carlo prediction, this is that algorithm. The reason I left those line blanks is just to show you that there's not much difference between every visit and first visit. In fact, all you have to do is keep track of the states that you visited, and then down here you just say, hey, if I have visited this state before, then continue. Don't do the update for this state if I have, and if I haven't, then do the update, but then add this to the visited. Okay, so first visit MC is just saying, okay, only update it after the first time that I've seen it. All right, so we just showed Monte Carlo using Blackjack. We just showed Blackjack using Monte Carlo as an example. But one of the interesting things is that we talked about dynamic programming last time, and we said that we can use dynamic programming if we have a model of the environment. So why would we go through a game where we know a model of the environment, like Blackjack? It has very simple rules. We can code up the rules easily. Why would we have to go through this process of playing out millions of hands, etc., in order to solve Blackjack? So the thing is, even though we do have a model of Blackjack, it would be very difficult to compute values for Blackjack using dynamic programming, even though we do have that model. And the reason, and we looked at this last time, is because I need to know the state transition probabilities. And so this is very hard to know in Blackjack. For example, we are required to know the distribution of next events and rewards, so I would need to be able to tell you with 100% certainty, if I'm at state 13.7 and my action is stick, what is the exact probability of terminating with a reward of +1? Right? So with dynamic programming, not only do you need the model, but you need to know what are the state transition probabilities as well. And for games with randomness and very long chains of things like hands and Blackjack, that can be very difficult. And so these things must be known in order to use dynamic programming, and that's a bit of a pain in the butt, right? So we would basically need to solve Blackjack before we try and solve Blackjack using dynamic programming. And so it's not really a fruitful effort. And so the cool thing about Monte Carlo is that you don't need it, right? You don't need the model. You don't need the all these state action transition probabilities. You just do sampling. You just play the game and you learn from that. So now that we have those state values, how do we form a policy, right? Because again, The whole point of reinforcement learning is to get a policy, not just the values of states. And so without a model, we can't tell which actions lead to other states just using samples. And so what we have to do is, up here, now that we have state values, that is assuming that we've calculated v of s, just the value of a state. And what this is saying that is if all we do when we do reinforcement learning is calculate the value of being at a state, we don't know the value of actions, so we don't know which action to take. And what we want is which action to take. So in practice, we have to calculate the value of doing an action at a particular state instead of just the value of the state itself. So in practice, we very rarely use those v pi of s calculations, like what is the value of a state, because it doesn't give us the necessary tools to actually form a policy. And so typically what we do is we do q pi of sa, and then if we know the expected return when starting in a state s, taking action A, and then following a policy, we know the value of an action. So whenever we're at a state and we want to know which action to take, we just look up q s of A for each A and take the argmax. And then, okay, we have the action that led to the highest value. Okay, so that's essentially Monte Carlo methods for reinforcement learning. That's how they work, right? You just take a bunch of samples, you play out a bunch of episodes, and then once the whole episode is done, you go back to each state and you update based on the end reward. However, for many problems, the number of states and actions is quite large, very, very large. So if we follow a given policy, we'll do the same thing over and over and over again, right? We won't be exploring very much. So we must be careful to explore, to choose actions and states that we haven't done before. And also explore with the states, so sample from states that haven't been visited yet. So what I mean by this is let's take the example of a game of checkers, or chess. Let's do an example of a game of chess, right? If you were teaching, using reinforcement learning, a computer to play chess, then what would happen is, maybe if you started it off with some example moves, etc. So if you've ever played chess, hopefully you all know the rules of chess, right? What is a typical opening move in chess? Anyone? Yeah, moving a pawn up, right? So moving one of your pawns up 1 or 2 spaces, typical opening move. But, for example, in a game of chess, you probably wouldn't move your leftmost pawn all the way up, or your rightmost pawn all the way up, because there's this idea of developing pieces in like the center of the board, and over the course of many, many millennia of playing chess, or many centuries or whatever of playing chess, humans have figured out, hey, it's a pretty good thing to move pieces closer to the center of the board than out the edges of the board. So what this is saying is, if all we do, like for example, if the policy that we were given to start off with was like a human-like policy, we're never going to see what happens if someone does move one of those pieces over on the side of the board, right? And this has happened before. Reinforcement learning trained systems, which were trained on expert human data as a starting point, learned to be very, very good against expert humans. But then we play against someone like me, who's bad at a game, and I make a complete blunder, and they've never seen that state before. And they don't know what to do at that state. And they make some crazy move because they've literally never been in that position. And there's so many stories of this happening in reinforcement learning where it was like, hey, this can come close to beating the world champion, but it couldn't beat Joe from down the street because it completely exploded because it didn't see it. One of the bad parts about learning is that you have to have learned it at some point, right? You can't just rely on search to search over everything you can possibly do. So search is good in that respect, that you don't need to have encountered something before in order to do a good move. But, so what this is saying is that during your training step, or during your training phase, make sure that you take actions and you explore. So we looked at some different ways of exploring last time, right? Don't always take the greedy action. Maybe use some epsilon greedy stuff. Maybe use UCB when you're choosing your action, even in reinforcement learning. And not only that, but maybe sequences of actions that you can take won't lead you to certain states very often. So you should also randomize the starting state that you get into, right? So for example, if your reinforcement learning algorithm is really good and it only ever plays games where it wins, and now it's in a situation where a human is really good and now it's losing, and it's never been in a situation where it's losing before, it doesn't know what to do. So start it off sometimes at the starting state of chess, sometimes in a losing state, sometimes in a winning state. Vary the states that you start in. In a game like Blackjack, it's very unlikely, for example, that you get dealt 2 2s for a sum of 4, right? So if you think about it, summing numbers that you get dealt from a card actually follows a normal distribution. So it's very likely you'll get something like a 10 sum to start the game with. But it's very unlikely that you'll get really low numbers, and it's very unlikely that you'll get very high numbers to start a game. And so what this would say is that if you are going to go learning in a game like Blackjack, then make sure you're not just shuffling the cards and dealing every time, because then you'll have a normal distribution over your starting states. Try and take every possible starting state, and then maybe just try each one, and then learn from that starting state. So you get a good sample of all the different actions that you could do at all the different states. Because if you don't, then there are certain state action pairs that you've never tried, and so you don't know if they're good, right? Just like when we talked about exploration versus exploitation, there's that restaurant down at the end of Kenmount Road that you never tried before, and it might be the best thing in the world, it might be the greasiest old garbage. You don't know because you've never tried, right? No offense to any actual restaurants on Kenmount Road. Okay, so now that we have the values, how do we update the policy? Well, it's the exact same thing that we did for bandit action selection. It's just taking the state action values and updating the policy based on that. So wherever we talk about getting values, so estimating values is called prediction, and then getting the policy update is called control. So we've seen how to estimate values given a fixed policy, but now how do we update the policy to perform better over time? So by learning the values of QSA over time, we can then learn a policy that approximates the optimal policy, and this is called policy iteration. So once we have a value estimate, we update the policy with respect to those values. So the things that had the higher values, we want to do those. And this is called generalized policy iteration, or GPI. And this will there'll be definitely some sort of question on the exam about this, because GPI is essentially reinforcement learning in a nutshell. So in GPI, we maintain estimates of both the current value functions as well as the current policy estimates. And the value function is repeatedly updated to more closely resemble the true value function, and the policy is repeatedly improved based on that value. Okay, so we've seen that a number of times already, but here it is on one slide. Policy iteration consists of 2 processes. Policy evaluation, meaning making the value function more closely estimate the value of the current policy. So we take the policy, we carry it out, and we evaluate that policy and update our beliefs. That's the value part, or evaluation part. Then the second part is policy iteration. Now that we've updated our beliefs of the values of state action pairs, we make the policy greedy with respect to the current value function. Okay? So in policy iterations, these two processes alternate, and then GPI refers to the general idea of letting PE and PI interact to improve a policy over time. And almost all reinforcement learning methods resemble some form of generalized policy iteration. There are some methods of reinforcement learning that only work with the policy. So they just see, okay, if this action, for example, let's not look at values at all. Let's just take the policy, carry it out, and then the action which did the best, we'll just update that to be a higher probability. Those are other methods we're not going to get into. But most reinforcement learning methods resemble GPI. So over time, 2 important things are happening. The first thing is that the values approach the true values, because as we do something more and more and we average it, we get closer and closer to the true value. And then because our values approach the true value, our policy approaches the optimal policy. If we knew the exact values of doing all the actions at all the states, we just pick the highest one, and that's the optimal policy. So when these processes stabilize, meaning there's no more changes, then the process is completed and we've converged to our optimal solution. So down here, I like this particular diagram where up here, these are the values, and down here, this is the policy. So we start at some particular point in value and policy space, and then we carry out the policy, and we get a new value, right? Then we update the policy to be greedy with respect to those values. Then with that new policy, we evaluate it to get new values, then we update the policy, and over time, we get closer and closer and closer to the true values, and therefore the optimal policy. Okay? And in the iterative sense, what's happening over here is that we take a policy, we evaluate it, and so V are our value estimates, or our QSAs in practice. And so our values approach the true values of V pi, and then once we have values, we update our policy to be greedy with respect to those values. So evaluation, improvement, evaluation, improvement, evaluation, improvement. So with Monte Carlo, how are we going to apply iteration within Monte Carlo methods? So policy evaluation, we just update the value estimates after each episode has been generated. And policy improvement, we update the policy based on the new value estimates. So again, just another way of looking at it, pi 0, this is our initial policy. Then we evaluate that initial policy to get a value estimate of that policy. Then we take the value estimate of that policy to improve our policy, and then it repeats again. So based on the new policy, evaluate, new values, improve, new policy, evaluate, new values, improve, new policy. And pi of s, that is the thing we should do at s, the action we should take, is just the argmax of QSA. So this means take what we believe the state action pair value to be, look over all the actions and take the maximum one, and then stick that into the policy. So finally, here is the algorithm for this MC policy iteration. We are going to start with some initial value estimates, and then we have some initial equiprobable policy or some other policy that you've read in from a file or online or somewhere. So we start with some values. Maybe those are all zeros. Maybe they're randomized. Not sure. Start with a policy. And then while true, this is the generalized policy iteration loop. We generate an episode based on that policy. We update the estimates based on the returns. Then we update the policy to choose the actions with the maximum values. And then over time, while this keeps looping, Q estimates the true values and P estimates the policy. So if we do this with Blackjack, then we end up getting one of these policies, if we print it in a very pretty way, where it says, if this is the card that I have, or this is the sum that I have, and this is the card that the dealer has, then what should I do? Well, I should either stick or hit based on the things that I've learned, right? So what you'll see, this is the policy view of this, but if we had the QSA view of this, for example, it might say, if I have 14 and the dealer has a 6, maybe the value of sticking is slightly better than the value of hitting, because it's on this boundary here. So right here, over time, it might say, hey, you've won $1.2 million by sticking here, but you've only won $1.1 million by hitting here, right? Or won or lost, or however you want to view it. So you've done slightly better by sticking here than hitting, and so you should stick here. And that's all it is. It's just play millions of hands of blackjacks, record the episodes, update the averages, and then update this based on the value of that. Okay. So I said you want to, what did I say? Let me remember. You want to visit all the states, right? And sometimes just exploring with actions isn't enough. So there's this idea of exploring starts. So many problems have large state and action spaces, and in practice, many state action pairs will not be visited very often, right? And so when generating episodes, it's important to vary the starting states, if possible, to ensure that all states get sampled. And this process is called exploring starts. And so in Monte Carlo, with exploring starts, all returns for state action pairs are simply accumulated and averaged. And the cool thing is, Monte Carlo with exploring starts, meaning that we are guaranteeing that each possible starting state has an equiprobable chance of being selected, it cannot converge to any suboptimal policy. That's a pretty strong statement, right? It cannot converge to a suboptimal policy. Now, it's not guaranteeing that you're going to find the optimal policy quickly, but anything we get toward with Monte Carlo exploring starts will be going toward that optimal policy. Here's why. Because if it did converge to a suboptimal policy, then the value function would converge to the value for that policy, and then the policy would change. Just think about that. If it found a bad policy, it would start doing the bad policy. We'd start to get less reward. The values would update, and then the policy would change. So if we're doing something suboptimal, we'll eventually figure it out and switch to doing the optimal thing. And so convergence to the optimal policy is intuitively inevitable as time goes on, but I don't have a proof for this. So proving this is difficult, but intuitively it does happen in most cases. So in practice, Monte Carlo with exploring starts, it does converge, but it converges slowly because not enough states are visited. And so what we can do is also explore while generating the episodes using epsilon greedy or UCB. So by including those randomized actions, so we have randomized starting states and some randomized actions, we get more actions and more states get visited, more actions get sampled, and we learn more quickly. So just as an overview of what we did so far, Monte Carlo methods use sampling to generate individual episodes, which are sequences of states, actions, and rewards. The value function estimate is updated at the end of each episode and with the rewards that it obtained. The policy is then updated to reflect the new estimates. So this is the generalized policy iteration part. And then new estimates are generated with the updated policy. Varying the starting states with exploring starts and action selection can help visit more states and converge to the optimal policy. So let me skip this real quick, and then I'll come back. And so some possible exam questions here. Define Monte Carlo methods. We have the Monte Carlo algorithm, V of S versus QSA. Given some samples, perform the Monte Carlo calculation. What is exploring starts, the definition of GPI, and this video. So what I'm going to do now in class is we have some time. I'm going to play this video I think is like 15 minutes long, but the important part is like the first 5 or 6 minutes. So I'm going to play the video here, but I will cut this off of the lecture because I don't like posting other people's YouTube content back to